function, the little f here? It's the exponential function e, right? What's being plugged into the e? Negative 3x plus 1. Is that linear? This only works if this is linear, okay? If that's linear, then I know that the antiderivative of this will be 1 over a, which for us would be 1 over what? Negative 3. And then whatever the antiderivative of this is, like e to something. What's the antiderivative of e to something? Itself. E to that something. And we're done. It just saves you the step of having to do the u sub. All right? It's not on the formula sheet. It's not in the book either. I don't know. It's just something that you could, I guess, do enough of these, you figure out that always works, right? How about this one? So what is the little f? I'm trying to trick you here. What's the little f? 1 over something, right? Like 1 over u, you could say, right? 1 over something. And that something is linear, isn't it? That something is linear. So you're looking at this as being something like 1 over u, right? And the thing that's in there, right? The thing that's in there for u is linear. So do you know the antiderivative of 1 over u? Natural log of the absolute value of u, right? But you're going to need to scale it by 1 over a. So this is going to become 1 over what? 4 natural log of the absolute value of what? 4x minus 3. And if you don't believe any of these, just take the derivatives of them and you'll see that the reason we need, right, the reason you need this 1/4 out here is because when you take derivative of this, chain rule is always going to spit out a what here? When we do chain rule derivative of this, we're always going to have to take derivative of what's inside, which is always going to produce a what? Here, 4, right? And I'm going to need to kill it. When I take chain rule on this, right, derivative of what's up here, I'm going to get a negative 3. I need to kill it off, right? That's what the 1 over a is doing. It's always going to kill off that constant that pops out with the chain rule when you're doing differentiation. Okay, that's it. That was our little detour. Back onto the highway, all right? Let's do that problem. It's very similar to the problem we just did as our first example of integration by parts. I'll change it. How about I change it a little bit? Let's do this. Integral, bless you, x cosine of 10x dx. You first have to convince yourself that there's nothing you can do here, right? Is there anything you can do, like using any other techniques or anything? No, right? Basic U sub? I mean, I'm saying no, but do you see that you can't do anything else? Do you all see it or not? That integration by parts is the only way to go. All right, so if I'm going to do integration by parts, I'm going to make a table. I'm going to pick a u, I get to choose, and a dv. Everybody have their u and their dv? Okay, who wants to tell me what u they're going to use here? Raise your hand. What are you going to use?
Still x because it's going to disappear.
Yeah, so you're going to use x because in the new integral, it's going to become a 1 dx, right? Or basically disappear because it's going to become a 1, right? So it's not going to get more complicated. It's going to get better. I like that idea. And that forces the other one to be whatever else was there. But you better know how to find the antiderivative of this, right? You better know how to go up on this table and get v. Differentiation, right? The differentiation should be the easy part coming down. This is going to be 1 dx, right? But you have to integrate this, right? Find the antiderivative. And isn't that what I just showed you? Right? This is going to be 1/10 sine 10x, right? Because we have cosine of a linear expression. So this will be 1 over 10 sine 10x plus c, but we'll get the c at the very end. Yes? No? Yeah? Okay. All right. So I like to always look now at voodoo. I like to look at this, which is going to be this times this, and I think, can I integrate that? So if I had 1/10 sine 10x times 1 dx, is that an integral that I can handle? And it is, all right? Let's see it though. Okay, so this equals, all right, here comes the ultraviolet minus voodoo. Ultraviolet, I multiply these two together. When I multiply these two together, I get, let me put the constant in front, 1/10 x, and then sine 10x. And then minus the integral, I'm going to put a space in front, minus the integral of voodoo, right? So voodoo is going to be this thing times this thing. I'm going to multiply those two together, and that's going to become my new integral. When I multiply these two together, what constant am I going to have? 1/10. Can I pull that constant out of the integral? I'm going to do that right now. I'm going to pull the 1/10 out. And then the only thing I have that has variables in it is the sine 10x dx. Questions? Do you know how to do this? The antiderivative of sine of a linear expression, right? Do you know the antiderivative of sine? Negative cosine. That's linear, right? So I'm going to need a scale again, 1/10. But I already have a 1/10 out here, so I'm going to have two 1/10s together. So here we go. 1/10 x sine 10x, okay, minus 1/10. Okay, I'm actually doing the antiderivative now, so no more integral sign. The antiderivative of this is 1/10 cosine 10x, and then plus c. This is going to be 1/10 x sine 10x minus 1/100th cosine 10x plus c. I'm not going to check the answer. I'll just multiply those together. Any questions? Yes? Am I missing? Am I, wait a minute, hold on, what did I? Oh yeah. I saw the looks on your faces. The antiderivative here, right, is negative, right? And then that'll change that to plus. My mistake. Maybe I should have checked the answer. Then I would have known I got something wrong, right? Yeah. Yeah, no. I'm a little distracted up here right now. I don't appreciate people sleeping in class or falling asleep. It kind of annoys me. So I'm a little distracted. When people are sleeping in class, then that's when I call on them. Because if you know how to do this and I'm putting you to sleep, then that's one thing. But if you don't know what I'm doing and you're sleeping, that's another thing. So, let me see, wrong mouse. Okay. Here's one not so obvious. The arc sine of pi x dx. I'm going to let you look at it for about 20 seconds. Does that feel like 20 seconds to you? So this is in my notes, and it says next to the problem, what does it say? A not so obvious integration by parts. So this is an example. This is only our third example, and I'm already giving you something that already does not look like what we've done, right? What is the thing that you're seeing that's way different than anything like the two problems I've given you before? We don't have like two distinct things, do we? We don't really have like two distinct things. Okay, well, we're getting ahead of ourselves. Let's make sure we can't do this with anything we know already. So this is obviously not x to a power, so we can't use a power rule. Basic u sub. No, okay? Well, do you just know the antiderivative of that? No, you know the derivative of it though, don't you? Like we learned that beginning of class. What's the derivative of inverse sine of something? So we know the derivative of it, we don't know the antiderivative, right? Okay, well, then all we have is integration by parts. That's the only other thing that we know at this point. So I'm going to make a table. And I'm going to have to force a u and a dv to appear here, right? And so what I want you to see here is that we actually do have two things. We have inverse sine of pi x times 1 dx, right? 1 dx. So I'm going to choose my dv to be the 1 dx because, well, dv is the derivative of something, and so I'm going to just have to use dx there as my dv. And that forces u to be what? Sine inverse of pi x, right? Now, the good news is that this stuff fits into my table, right? It fits there. The bad news is that I have to differentiate this and integrate this. Well, let's do this one. This one's easier, right? What's the antiderivative? Careful. What is the antiderivative of 1 with respect to x? X. Just x. Just x. Right? Because think about it. What's the derivative of x with respect to x? 1. So the antiderivative of 1 with respect to x is x. Okay, well, I'm not too terrified to see an x there, right? That, though. What's the derivative of that? Well, we went through this, right? You're going to have a test on Monday, and that I could ask you for the derivative of that, right? That would be more than fair. du, giving myself some space, is, there's a formula for it, right? It's 1 over the square root of 1 minus x squared, right? But what do we have? We don't have x, we have pi x. So it's pi x squared, and then you have to finish with the chain rule. What's the derivative of what's inside? Pi, that's a constant, right? Pi dx. Did you all see where everything came from there? And then you look at that, you're like, shit, my new integral is voodoo, right? My new integral is going to have voodoo. And when I look at this times this, when I look at it initially, I'm like, oh my gosh, that looks horrible, doesn't it? Like it's got square roots in it. Looks terrible, yeah? But this is it. This is the only option we have. You can't do your table, let me put it here. You can't do this. We could not have done this. I think it'll be obvious when I do it. You couldn't have done it the other way around. If you put the sine inverse of pi x, you have to put the dx here, right? You would have to put, this has to be the derivative of something. So if you choose to do the sine part with the dx there, then the only option you have for u is what? 1, right? And then you have two problems. What's the derivative of this? 0. So your new integral is not going to be there. And then the bigger problem, what's this? The original frickin' problem. You know, so like you're not going to do that, right? Do you see that that's the original problem? So yeah, this is not going to work, right? So that's like the only choice we have. So we need to proceed with this. All right, so I'm going to write things out. Using the formula, ultraviolet, right? Ultraviolet minus integral voodoo, right? So this becomes ultraviolet off of this table is these two multiplied together. So I'll put the x in front of the inverse sine of pi x minus, leave some space. Okay, voodoo. All of this times that is what goes into the new integral. When you look at these two, are there any constants that I can pull out of the integral? This pi, right? That's a constant. So that pi can come out of the integral. I'm going to pull that here. That pi is not there anymore. And then everything else is still there, right? I've got this x. I've got this 1 over this, yeah? I'm going to write that all together. I'm going to put the x on top of the square root of 1 minus, and I'm going to, bless you, I'm going to go ahead and decide to square this right now. That's pi squared x squared dx. Take a look. Any questions where I got any of this first?
Did you get the x in the top right?
Right. Oh, here? So I'm taking this, right, and I'm multiplying times this, right? So I'm doing 1 over the square root of 1 minus pi x squared dx, right? That's this. And I'm multiplying that times x, which is this, right? And then I'm just sliding the x on top. Do you see it? Okay. Everyone good? Okay, now, I'm telling you there's a way through this problem. You've got to see it now. So don't blurt it out, but raise your hand if you see what we need to do next. Does anyone see what comes now? How to handle that integral? You see something? Don't say it yet. You think you see something? Okay, good. Anyone else? You think you see something? Okay, we got 3 people, 4, maybe 5. Do you see it? All right, so I'll take a volunteer, but I want to try and pick someone. Do you want to? Because you haven't. Do you know what?
I saw tangent.
Oh, so you're thinking the 1 over. You're thinking of the arctangent formula, okay? That won't work because of the square root, and plus this needs to be a plus. In the formula, it's a plus, right?
Oh yeah, you're right.
Right, and there's a root, so we can't use that. That's all right. Look, trying to explain to my daughter yesterday, she's taking geometry, and she was like, yeah, these kids in my class, like, some of them, they just don't get it. And I'm like, look, you learn by making mistakes. Like I said, right now, maybe you're not making mistakes, but you will make mistakes. Like, that's the way we learn in math, especially in a class like this. You're going to have to make mistakes. Mistakes like trying the wrong thing and then realizing, hey, that didn't work, right? So it's okay. You're going to fail. As you're learning, you're going to fail more than you succeed on these problems. You'll have to start over. Start the problem over. I would recommend that when you're doing your homework, every problem you work out, if you get to a point where you're done, you're going to try something new, don't crumble that up and throw it away. Keep it and say this didn't work, move, and then try it again. Because you might have like 5 attempts and then realize, holy shit, I'm doing the same thing, I just threw that away, right? It'd be good if you had all your work together so you can say, yeah, I already tried that, let me try this, right? It's persistence, over and over trying something. All right, you raised your hand?
Could you like subtract the constant and then take the square root of each of them?
So you can't do the square root individually because there's a minus between these. If
They're both constants.
I'm not sure I understand what you
I
mean.
mean, they're both,
Squared?
yeah.
Whenever you have a square root of terms, you cannot do the square root of each one, no matter what. You can't split it up. Okay, who else said they thought they had it? You think so? All right, what do you think?
Can we use substitution?
Use substitution. That was last class. See, you have a new integral in front of you, right? You have to start over and you have to say, what are the techniques I've learned to solve integrals, right? And you look at this and you say, okay, let me try use substitution. So do you see something in here? And also you see its derivative there as well. The derivative can't be trapped. It has to be in the numerator, right? So what do you see as the thing that you're going to call u?
1 minus pi squared x squared.
The whole thing in here. The whole thing, right? We're going to do u sub right now. And the u we're going to use is 1 minus pi squared x squared. Why? Take the derivative of this. What's the derivative of this?
Negative 2 pi squared.
Okay. Yeah, so the derivative of 1 is 0, right? Okay, minus, okay, pi squared is a constant, right? So just bring it for the ride. What's the derivative of, I can't talk, of x squared? 2x. So this is going to become minus 2, that's from the 2 coming down, the minus there. Pi squared is a constant, and then x dx. If it feels like you've kind of stepped into another world today, like in terms of like the expectation and what you're, it's hard to prepare students for how quickly this class gets challenging, right? It's like you needed to really be good at U sub to see this. Like you need to be real comfortable with it, right? Which was last class. And then next time we meet, you need to be really good with integration by parts. So it just builds so quickly, which is why you've got to do your homework, you've got to get help, ask questions. All right, does everyone see it? If we let u be what's underneath the root, the derivative of it's right here. All of this is a constant. I have x dx. Do we see x dx there? Yeah? See the x dx right there? Different color. See, we have x dx right there, and that's this piece right here. So we're just going to divide both sides by this, and then we should be able to rewrite the integrals. All right, so what I'm going to do, because this is going to start getting complicated, I'm going to step to the side here and do some scratch work. And my scratch work is actually going to be the integral I'm looking at right now. Because I think it might be a little bit too complicated to kind of put it all together over here. I'm just looking at from here on. And I'm going to go do that and figure out what it is. And then once I'm done over there, I'm going to bring it back over here. All right? All right, so we're making this u substitution. If I make that u substitution, let me solve here. I do 1 over negative 2 pi squared du equals x dx. So all I did there was divided both sides by negative 2 pi squared. And that tells me what I'm going to replace my x dx with. So this integral becomes, right, what does the x dx become? What does that part become? All that, right? Is it all right if I write it like this? Bring that whole constant out, and then just put the du in the back. That's me replacing the x dx right here with all of this. The constant is going to be pulled in front of the integral, and the du I'm just pushing to the back. What's still here, though? You have a 1 here on top of this root. This root is now root of what? U, because we call this thing, right, this right here, was u, right? So this is 1 over u. Say? Yes,
So are you ignoring like everything that's below that?
Yep. I'm doing scratch work. I'm saying I'm just working on this right here. Okay, that's my scratch work right there. Everything I'm doing over here is just this one piece. I'll have to remember there's a minus pi in front of it later. All right, almost ready to do the antiderivative. I'm going to rewrite that. That's not natural log, right? I have to do u to the negative 1/2, bring it up. Right, I'm going to use power rule here. Bring that up, and now I can use the power rule. So I add 1 to that. What's 1 plus that? 1/2, and then out front we'll need the reciprocal, so 2u to the 1/2. And now I'm at a point where I could say plus c. You see how everything is really like building on itself pretty quickly? Like you've got like power rule that we did earlier, and then there was u sub, which we did last class. So everything depends on what we did before. All right, here we go. We're here. These 2's go away. And I can rewrite that as negative 1 over pi squared. This is really the square root. That's what that means, right? And what was u? 1 minus pi squared x squared plus c. That's my answer to just the part that's dotted there, right? So now I'm going to come back and give you a final answer. My final answer is, coming back over here, I'm going to continue from this. I'm going to put it right here next to this. Equals, okay, it's this part right here, x sine inverse of pi x, right, minus pi, that's this, and then that, which is times negative 1 over pi squared, and then square root of 1 minus pi squared x squared, plus c. There it is. Now I can clean up a little bit more. I can see one of these pi's goes away. So I'm going to do that. I'm going to just get a final version here.
Can we do like that on the test?
Oh, you can. I'm not going to take off. It is correct, but it's also not that much more to go, just one more step. If you're worried about time, then yeah, absolutely. You get to that point, that's okay, move on. There it is. That is the antiderivative of the inverse sine of pi x. That means if we take the derivative of that, we should get what? Inverse sine of pi x. Should we? Check or no? Do I want to check? Let's check, because there's going to come a point where we're just not going to be able to check it. It'll take too long. Let's just do one check to make sure this is right. So I'm going to differentiate this, and I'm going to check to see that I get that as an answer. And when I go to differentiate this, I'm going to see that I have really just a product rule there to deal with, and then that's a sum, so I can do that separately. So here I go. Product rule here. Derivative of x is 1 times the inverse sine of pi x. Okay, plus now the derivative of inverse sine of pi x, which is 1 over the square root of 1 minus this thing squared, pi squared x squared, times the derivative of what's inside, which is pi, times the first function x. Finished with the product rule, plus 1 over pi is a constant, comes for the ride. The derivative of the square root of something is 1 over 2 square roots of that something, times the derivative of what's inside, but the derivative of what's inside is negative 2, derivative of what's inside, negative 2 pi squared x. Okay, I'm done differentiating. One of these pi's goes, the 2 goes. What do I have? Oh, that's it, I'm done. Do y'all see that? What is all this? That is negative, what's on top? Negative x over just that square root of that crap, right? And then what's this one? The same thing as that, except plus. Right? This and this are exactly the same, just that one's minus, this one's plus. So these are gone, which leaves you with that, which is that. So it works. Okay, we're done. We're moving on. It's reassuring to know that we got the right answer. All right, how are we doing here time-wise? All right, we've done 4 problems. That one took a little while, yes? Let's see what our next example looks like. That screen timed out on me. These are like complex puzzles that you're trying to figure out, right? What is the independent variable in this integral? What's the independent variable? T. So our variable in the problem is t, not x, all right? That's just to show you, I mean, we can always change our independent variable. It can be anything we want. Now this right here, that's beta. That is I'm telling you that is a constant, but I'm not saying what it is. So beta could be like the number 4. Or the number 10, or any number you want, right? But in this problem, we're just going to leave it as beta.
Like C.
It's like a C, exactly. Normally, the reason we are using beta is because, in pre-cal for angles, we like to use like alpha, beta. And since it's the argument of a trig function, it kind of makes sense that it would be beta as an angle. All right, you ready? First, we eliminate any other thing that we could try. Hey, wait, u sub. What about u sub? What if I take u to be t squared? What's the derivative of that? 2t, and I have beta t, right? Isn't that off by a constant? But what's wrong with it's inside a cosine? Don't want to do that, right? So I don't want to do a u sub. Yeah, okay. Integration by parts is pretty much all we've got. U dv. What are your thoughts for u? Thinking t squared? So if you let u be t squared, in the new integral, it'll be 2t, right? So we're saying if we let this be u, in the new integral, we're going to have 2t. And then we're going to have the antiderivative of this. Do you know the antiderivative of this? It's going to have sine, but look, this is like a linear expression. You'll have 1 over beta sine beta t. Isn't that what you would have? See, I'm trying to like think ahead before I fill out my table of what's going to happen. So what I'm writing here is actually what I'm thinking, all right? I'm saying if I let u be this, the derivative of that's this, and then the antiderivative of that is this. And now I think about, could I do this? No, right? Because I still have a t here, right? So I can't do it because I still have a t. But what could I do? Do it again. Do integration by parts on this new integral a second time. So we're going to do an integration by parts within an integration by parts. So when we get our new integral, we're going to say, hey, that new integral, if I let that be u and let that be dv, the derivative of that will be a constant, antiderivative of that will be a cosine function, and that I can do. You see, this is going to be a repeated integration by parts problem. We're going to have to do it twice. All right. So let's let u be t squared. Why not the other way? I didn't talk about that, but why not put the t squared here? And then put the cosine beta t here. Well, if we put t squared here, what's this? 1/3 t cubed. And then this voodoo is going to have a t cubed and what, a sine or cosine in there? That's actually worse than what we started with, right? Because we started with a t squared. Yeah, so let's just go with this. So this is, fill out the